Everybody loves pizza. To make a pizza that everybody loves, you have to start with all the right ingredients. But even more importantly, these ingredients have to be combined according to a tested recipe. And the same is true for good data. It's the method that matters. In this unit, we'll be examining some tested recipes for generating data. We'll distinguish between observation, which is looking without interfering with what's going on, and experiment, which is actively intervening in order to see some consequences. We'll see that both observation and experiment can go wrong if other influences are mixed up with the factors we want to study. We call this mix-up confounding, and try to avoid it as much as possible. And we'll look in detail at the all-time favorite recipe for producing good data, the randomized comparative experiment. A researcher's first task is to observe, to understand as much as possible by carefully watching subjects, here lobsters, behave as they would normally. But what's normal to a lobster may be mystifying to a human being. By watching, Diane Cowan identifies patterns in lobster behavior before making hypotheses about what those patterns might mean.
At night, they're very active and very exciting, and these tanks have a soap opera going on all the time. So it's no problem to watch them for hours and hours.
Lobsters spend a lot of time walking outside of their shelters but not feeding. Why do they expose themselves to danger in this way?
Our interpretation is that they need to know about their physical and social environment. They need to find out who lives where.
Their list of priorities goes shelter, mates, and then food. So it's very important for a lobster to have a shelter.
Shelter is so important, in fact, that lobsters fight for it.
Okay, she just won that fight. She kicked the other animal out of her shelter just by hitting her in the claws. Now they go in head first, check it out, turn around, and back into the shelter.
There's a lot to learn about these crustaceans if you just have the patience.
If you sit, don't think, just watch them. They'll tell you about their lives, and then you can ask legitimate questions, formulate a hypothesis, and then test it. It's critical to watch them first.
Once we've learned from observation which questions to ask, we can improve our data by intervening. For example, observation shows that lobsters rely heavily on their acute sense of smell. To see how well they function using smell without vision, food coloring is added to the tank. Researchers continue to observe, this time comparing behavior in clear and opaque water. Now we're conducting an experiment. Unlike observation, in an experiment you actually do something to the subjects, lobsters or people or anything being studied. What you do to the subjects is called the treatment. The purpose of an experiment is to observe and measure the effect of the treatment on the subjects in a study. Each year, 1.5 million Americans suffer the trauma of a heart attack, and more than a third will die, most even before they reach the hospital. In the early 80s, an ambitious long-term experiment called the Physicians' Health Study was designed to address the problem of heart disease in the United States. Heart attacks occur when clotting blocks the flow of blood to the heart. Observational studies suggested that aspirin can help prevent blood clotting, lowering the risk of heart disease. But to confirm the effects of aspirin, it was necessary to go beyond these observational studies.
There were two lines of evidence that suggested the possibility that aspirin might prevent heart attacks in healthy people. One is the basic research that suggested that low doses of aspirin would inhibit the tendency of blood platelets to stick together and therefore inhibit clotting. And the second was some observations in human populations that suggested that people who used aspirin regularly might have lowered risk of heart disease from those who did not.
The goal of the Physicians' Health Study was to put the observed effect of aspirin to a more rigorous test.
Dr. Clemens, this is Patricia Alexander with Dr. Hennekens at the Physicians' Health Study in Boston.
The yearly rate of heart attack in men between the ages of 40 and 84 is just 4 per 1,000. So many subjects were needed to have enough instances of heart attack to be able to draw a conclusion. 22,000 healthy male doctors were chosen for the study. Dr. Bernard Katz is one of the study subjects.
I chose to be in the study because heart disease, which is the nation's #1 killer, as we all know, is something that's of personal interest to me, not only for my patients, but for my own welfare, my family's welfare.
Half of the subjects, the treatment group, took aspirin every other day. The other half, the control group, were given a dummy pill called a placebo. The physicians in the study didn't know whether they were taking aspirin or a placebo. The medical personnel who worked with them also didn't know. This is called double blindness. Now, why complicate the design by having half of the people take a placebo and the other half take aspirin? Why not have all the subjects take aspirin? Well, the subjects knew they were in a health study and were being carefully watched. This knowledge could inspire them to change their habits. They might exercise more, for instance, or eat a lower cholesterol diet. So if, at the end of the study, subjects had fewer heart attacks than expected, it might have been due to the aspirin, but it also might have been due to factors outside the researcher's control. In other words, the effects of the subject's changed behavior would be confounded or mixed up with the effects of the aspirin itself. There would be no way of telling which contributed more to a reduction in the number of heart attacks. In order to avoid confounding, 2 groups of subjects are compared, all of whom take a pill regularly and are watched with equal care. Because half get aspirin and half get a placebo, and no one knows which pill he is taking, then changed habits and other outside variables affect both groups equally. The only difference between the groups is the aspirin. There's one more ingredient necessary for a good experimental design. Remember, both groups are treated exactly the same except for the contents of the pill they take. But what if the groups were not similar to begin with? It's possible that the assignment process itself was biased, either intentionally or unintentionally. Imagine a sympathetic researcher favoring older or weaker subjects, assigning them to the aspirin group in order to help them out. Because these people are more likely to have heart attacks, the study results would be biased against aspirin. To avoid this, impersonal chance is used to assign subjects to groups. Young and old, weak and strong, all have the same chance of getting aspirin. Chance ensures that there's no systematic difference between the groups at the beginning of the study. The result is what is called a randomized comparative experiment. Let's recap the features of a randomized comparative experiment. Groups are similar to begin with because assignment is done by impersonal chance. Both groups are treated alike throughout the experiment except for the contents of the pills, which is unknown to both the subjects and the doctors watching them. The design ensures that whatever differences exist between the 2 groups at the end of the study can be attributed to the effect of aspirin. 5 years into the physician's health study, differences between the groups did appear in the research results.
There were 104 total heart attacks in those who were assigned at random to aspirin, and there were 189 heart attacks for those assigned at random to placebo. This suggests there was a 47% reduction in heart attacks in those who received aspirin compared with those who got placebo.
Given these findings, was it ethical to continue to withhold aspirin from the subjects taking placebo? Questions like this are always part of doing research on human subjects, particularly when a treatment is thought to be beneficial. In fact, it's one of the first issues confronting researchers when designing experiments with human subjects.
I think we have to have sufficient doubt about the agent being tested to allow us to withhold the treatment from half the subjects. But at the same time, there has to be sufficient belief in its potential to justify exposing the other half of people to the active ingredient.
After carefully weighing the pros and cons, researchers decided to stop the study. The code, information on who was taking what, was broken early, and subjects were notified of the results.
With my luck, I figured this thing really works. Naturally, I've been on placebo. But it turns out that I was on aspirin and tolerated it very well and plan to continue taking it indefinitely.
These results were very encouraging to people at risk for heart attack, but we have to be careful about over-interpreting them. While aspirin helps reduce the risk of heart attack, it cannot completely counteract other negative factors, such as lack of exercise or poor diet.
I think it would be tragic indeed if a middle-aged person, say a cigarette smoker, were to, instead of quitting, begin to take aspirin to try to reduce their heart disease risk.
By now, you should be familiar with the design of a randomized comparative experiment. But there's one more detail to cover, a practical point: how to go about assigning subjects to groups by chance. One way would be to use a roulette wheel. Another way would be to pick names at random out of a hat. But with 22,000 subjects, we'd need a pretty big hat and a lot of slips of paper. A more efficient method is to use a table of random digits. Such tables are usually created by computers. The computer randomly picks a number between 0 and 9. It does this until it has generated a long string of digits. Any one of the numbers is as likely to be picked as the next, as each is independent of the others. This table can be used to make random group assignments for any experiment we might conduct. We'll illustrate the principle on a small scale, say with 14 subjects. First, each subject gets a numerical label. Every label has to be the same length. In this case, we use the two-digit labels 01, 02, 03, and so on. Then, we read the random number table in groups of 2 digits. The first 7 names selected will be in the treatment group. The remaining 7 will be in the control group. The first pair of digits in the table is 12. The name that has the number 12 is Muir. The next pair of digits is 09. That's Watt. We jump over the gap for the next 2, 57. And that's not one of the labels. We had only 14 subjects, so we skip it. 69 and 41 aren't labels either. 14 is, so Riley is chosen for the treatment group. Continue through the digits until 7 people are chosen for the treatment group. You see the method. Because the digits in the table were chosen at random, the subjects who correspond to them are random as well. Randomized assignment is a critical design feature in an experiment like the physician's health study. Subjects were assigned at random to aspirin or control groups so that groups were as similar as chance could make them. Then these groups were compared. Both were treated exactly alike except one received aspirin, the other a placebo. Neither researchers nor the subjects knew who was receiving treatment and who received placebo. And the sample size, 22,000, was large enough to observe a reliable difference in the heart attack rates between the 2 groups. This is needed in any experiment. The sample size should be large enough so that the observed differences occur in sufficient number to count as convincing evidence.